So before going to the page ranking, we'll be seeing central closeness centrality. We'll be look at code closeness centrality. So closeness centrality is one of the centrality that is the shortest based centralities. We have seen between centrality, degree centrality, eigenvector centrality. I'm skipping here. So closeness centrality we'll discuss now. So let me discuss closeness. So what is closeness centrality? Closeness centrality of a node is the average length of the shortest path between the nodes. So I think you understand the closeness is nothing but the average length. That is, we have to find the mean of the shortest path between the nodes of between all the nodes. So let me write the definition. The closeness centrality of a node is the average length. You have to find the mean average length of the shortest path between the node and all other nodes. This is what is known as central closeness centrality. We have to find the shortest paths between each and every node. So let me take one. So the formula for central closeness centrality is given as closeness centrality of for any index or node is given as 1 by n is equal to sigma j is equal to 1 to n of degree of I comma j. So this is the formula for closeness centrality, where n is nothing but the vertices, n is nothing but the number of vertices, and d is nothing but the distances between them. So we have to find the shortest paths, right? So for calculating the shortest paths, we have to take the distances between the between the each and every vertices. So d of ij is the distance between each vertex. So we have to find the distance between each vertex for every vertex in the graph. That is here we got the summation symbol. That's why we have to find. Let me take one undirected graph, one directed graph and another directed graph, where we'll be finding all the closeness centrality. So let me take this graph, which graph we already taken, right? 4, 5 and 6. So don't worry that I am already usually taking the same example. So I thought it will be better if I explain with the same example in all the centralities. This makes you won't get confused for later purposes. For fun one, it is a directed graph. So for directed graph, so there is a one special condition in directed graph, that is, if there is a no path between any of the vertices, we will be replacing the distance between the huge of the count of the node or into 100. You will be understanding when solving the problem. So let me take the directed graph. So closeness centrality for the vertex 1 is number of vertices are there, 6 vertices are there. That is n minus 1 is formula, that is 5 by here that was the summation of distance between each and every node. So it is a directed graph, right? So for 1 to 2, how many edges are required? 1 edge is required. So for 1 to 3, we have to check for each and every possibility. 1 to 3, 1 edge is required. Excuse me. For 1 to 4, is there any edge between 1 to 4? No. So in that case, we have to replace the so in that case, if there is no path between any of the two vertices, we have to replace it with 100. So why 100? Because we are dealing with the probabilities, right? So probability should be between the range x lesser or equal to x lesser or equal to 1. So if this is not the probability condition, then the entire centrality will be wrong. So we have to make sure that our ranges will be in the between the 0 less than or equal to x lesser or equal to 1. So that is the main reason why we are taking 100 here. So let us try to find for 1 to 4. We have completed 1 to 6, no path, so replace with 100. 1 to 5, no path, replace with 100. So totally we will be getting a 5 by 302. So the result it will be in a 0 point something. So leave it. Now calculate for CC of 2. So CC of 2 will be, that is closeness centrality for 2 nodes. Second node, 2 to 1 it has one edge, 2 to 3 it has one edge. For 2 to 4 it has no edge, so replace with 100. For 2 to 5 no, 2 to 6 no. So here we will be getting 5 by 302. Let us calculate CC of 3. 5 by, that is the number of edges, number of vertices, by from 3. How many paths required to from 3 to reach 1? 1, 2. So 2 plus, for 3 to 2, 1 plus, 3 to 4, no, replace with 100. 3 to 5, replace with 100, no. 3 to 6, replace with 100, no. So we will be having a 5 by 303. So CC of 4 is equal to 5 by, so from 4 to reach 1, how many parts are required? 1, 2, 3 parts are required. 3 plus 4 to 2, 1, 2, 2 parts are required. 4 to 3, 1 part. 4 to 5, 1 part, 1 edge. 4 to 6, 1 edge. That is totally we got 5 by 3, 4, 5, 6, 7, 8. So 5 by 8 we got. Next CC of 5. Let us find the CC of 5. 5 by, what is 5? From 5 did we are able to go to any other vertex? From 5 we can't go. From 5 it is totally closed, we can't reach any of the vertices. So replace with 100 plus 100, 100 plus 100, 100 plus 100 plus 100, which relates to 5 by 500. Next let's calculate CC of 6. CC of 6 is nothing but 5 by, from 6 how many, from 6 the number of paths to reach 1, 2, 3, 4. 4 plus, for 2, 1, 2, 3, 3 plus, for 3, 1, 2, 2 plus, for 4, 1, for 5, 1. It is 5 by 4, 7, 8, 9, 10, 11. So 5 by 11. So this is the actual calculation for a closeness centrality. The actual process to find the closeness centrality for a undirected graph. Sorry, it is directed graph. So coming to the undirected graph, how we will be finding undirected graph. So for undirected graph, let us take this graph also. This graph itself, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So this is the undirected graph. So we will be finding the closeness centrality. So CC of 1 is equal to, same formula we will be using, 5 by, but here we will be calculating each and every distance, because there is no conditions, there is no restriction that from one node we can't move to the another node. So we will be having each and every node distances. So from 1 to 2 it has 1, for 1 to 3 1, for 1 to 4 2, for 1 to 5 3, and 1 to 6 it is 3, this 3 edges. So 5 by 3, 3, 9, 10. So 5 by 10. Next CC of 2, 5 by, why I am taking 5? The number of vertices are 6. So 6 minus 1. So here we formula 1 minus n minus 1. That is 6 minus 1 is 5. So that's why I am taking 5 for all the numerator. So for 2 to reach 1, 1 plus, for 2, 2 plus, 3 plus 3. That is 5 by 10. For CC of 3 it is 5 by 3. 1 plus 1 plus 1 plus 1 plus 1 plus, what is there? Next it takes only 2 steps. 2 plus 2, that is 5 by 4, 5, 6, 7. So 5 by 7 required. So CC of 4 is equal to 5 by 1 plus 1 plus 1 plus 2 plus 2. It's equals to 5 by 7. Next CC of 5 is equal to 5 by 1 plus 1 plus, CC of 5 we have taken 5, right? So for 5 to reach 1, 2, 3. So 1, 2, 3. 3 steps are required. For 2, 1, 2, 3. 3 steps are required. For 3, 2 steps are required. 2 steps are required. For 4, the 1 step is required. For 6, 1 step is required. That is 5 by 6, 7, 8, 9, 10. 5 by 10 paths are required. So let us move to the CC of 6. CC of 6 is equal to 5 by, for 6 it is 1, 2, 3, 3 plus 3 plus 2 plus 1 plus 1. So just calculate mindly, that is, it will be so easier with the while seeing the figure. So 5 by 10. So this is what actually we'll be doing in a closeness centrality. So what is closeness centrality? Closeness centrality of nodes is the average length of the shortest paths between the node and all the other nodes. So n minus general formula, n minus 1 by sigma j is equal to 1 to n distance of I node to the j node. So for the directed graph, there is a condition that if there is a no path between two vertices, we'll be replacing with the 100 or any other higher number. That is what we have seen here. So for an undirected graph, there is no restriction that based on the paths it is based on the number of edges or the distance it covers, we'll be dealing with the central closeness centrality. That's all for closeness centrality. Let's move on to the page ranking. So what is page ranking? Page rank is nothing but the number of links that a page rank will be having. It is not the number of it is the number of links. Based on the SEO, search engine optimization, the top of the pages will be displayed. For example, if you search page rank in Google, there will be a listing of top 1 to 10 or 1 to 12 websites which are ranked based upon this page ranks, because the number of which they are getting will be based upon this page ranks. So page ranks model will be of two types: random surfer model, and there is another model known as matrix model. Both are simple, but mostly we'll be using this page ranking based on the time we'll be having. So let us discuss random surfer model with an example. So what is random surfer model? Random surfer model is nothing but they will be using page ranking of A as well as the inbound and outbound links to calculate the page rank of each and every node, each and every node or the page. So let me define random surfer model. So random surfer model formula they will be giving as page rank of A is equal to 1 minus d plus d of PR of T of I by C of T of I plus so on, plus PR of inbound by C of inbound. So this is what the formula for random surfer model. I will explain what it is. PR of A is nothing but the page rank of A. Next, PR of T of I is nothing but page rank of pages T of I. Page rank of page T of I which link to the page A. So next one, C of T of I is it is the number of outbound links, on page T of I. And D, what is D? D is nothing but the damping factor which they will be providing in the question itself. So D is a damping factor. Which can be set between 0 or 1, or there in question they will be given. Just try to make off note. If they didn't give it in question, you can use either 0 or 1. If they provide it in the question, use the D as a damping factor. So let us try to solve one problem. You will be getting what exactly the random model surfer is. So let me take an example. So A, B and C here. So I'm taking a very simple graph, because this random surfer model is very huge. we have to try to get the page rank for all the vertices, all the nodes, uh, till they be equal. That is what the random surfer model and page rank will be. So every page has to be same, equal preference has to be given when we are trying to trying it in a real time or in a theoretical or problematical manner. So for example, if A, B, C are the nodes, we don't know that how many times the page repetition will occur. So here we don't know the number of combinations or the number of steps which are required to get the uniqueness of each and every vertices. So let us take this example, and in the question they have given damping factor as 0.85 and initial page rank is 1. Initial page rank PR of I or the vertices V is given as 1. So now let us try to build the page rank model, that is random surfer model for each and every vertices. So let us take PR of A. Page rank of A is equal to 1 minus D, that is 1 minus 0.85 plus what is D? 0.85. Based on the formula we have to write the this one 8.5 of. So now we have to find what is T of I. This is nothing but the inbound. Okay, did you get that? Inbound is nothing but the number of incoming edges. So for A, what is the incoming edge? For A, incoming edge is coming from C. So we have to write the formula for C, that is PR of, that is T of I. Here T of I is nothing but C by C of C. Okay, I think hope you get it. How did I write the formula? So here PR of T is nothing but the inbound edges, and CF of T is nothing but the outbound edges. So PR of C is nothing but the inbound and C of C is the outbound vertices, outbound edges. So let us take your calculator and try to solve it. Just try to 1 minus 0.85, which results to 0.15 plus 0.85 of what is PR of C. PR of C is nothing but the incoming edges from C. How many incoming edges are there? 1 by number of outgoing edges from A. The number of outgoing edges from A is nothing C. So number of outgoing edges from C is nothing but C. So we will be getting a 0.15 plus 0.85, which results to 1. Therefore PR of page rank of A is equal to 1. So now let's try to find the page rank of B. PR of B. PR of B is equal to 1 minus 0.85, that is 1 minus D plus D 0.85 of. So let us see the image. The incoming edge which is from A. So PR page rank of A by only from A. So there will be next C of A, that is 0.15 plus 0.85 of. So the number of incoming edges from to B is 1 by number of outgoing edges from A are 2, that is 1 by 2 is equal to 0.15 plus 0.85 of 0.5, which results to 0.85 0.85 into 0.5 plus 0.15, which results to 0.575. So therefore page rank PR of B is equal to 0.575. So coming to page rank PR of C. So PR of C 1 minus 0.85 plus 0.85 of. So number of incoming edges are from A and B. So we have to write the formula for A as well as the B. So that is PR of page rank of A by C of that is the outbound links of A plus PR of B by outbound links from B. So that is, it will be 0.15 plus 0.85, What is page rank of A? We got page rank of A as 1 by what is outbound links for A? For outbound links of A are 2. So here for B and C. So 2 plus page rank of B we got as 0.575 by what are the outbound links from B? There is only one outbound link to C. So 1. So results to 0.15 plus 0.85 of 0.5 plus 0.575. So totally we will be getting a solution of 0.85 plus 0.5 plus 0.575 equal to into 0.85 plus 0.15. So we will be getting a solution of, so PR of C is equal to 1.06375. So did you see that we didn't get the equal values, that PR of A is 1, PR of B is 0.5 and PR of C is 1.0637. So we didn't get any constant value. So we have to do this level for another one. So this is known as level. So level 1. So we will now follow. Now we will be doing level 2. So solve for level 2. So let me take the figure again for our convenience. A, B and C. So we got page rank, initial page rank of A is 1 and page rank of B we got as 0.575 and page rank of C is equal to 1.06375. These are the page ranks we got in level 1. So now we will be seeing level 2. So in level 2 let us consider page rank of A. Page rank of A is equal to it is 1 minus 0.85 plus 0.85 of, so we have to consider number of outbound links, that is only from C. So PR of page rank of C by outbounds of C. So that is 0.15 plus 0.85 of, what is page rank of C? We got page rank of C as 1.06375. 1.06375 by number of outbound links from C. There is how many outbound links are there? There is only one outbound link, that is 0.15 plus 0.85 of 1.06375. So we will be getting a solution of into 0.85 plus 1.15. So we got 1.054185. So we have to take each and every decimal value to get the accurate page rank. So don't neglect any decimal value. So PR of A we got as 0.151875. Now let us find page rank of B. So page rank of B is nothing but 1 minus D plus D of, so from D we got only incoming is from A. So PR of A by C of A, that is 0.15 plus 0.85. I have written it directly. What is PR of A? PR of A we got as 1.054185 by what is CC of A? The number of outgoing edges 2. So let us try 0.15 plus 0.85 of, let us divide all this divided by 2. We will be getting 0.52709375 into, we got 0.85 plus 0.15, which results to 0.59802967. So page rank of B is that much. So now let us calculate page rank of C. PR of C is equal to 1 minus D plus D of PR of, so for C we have 2 incoming edges from A as well as the B. So we have to write PR of A by C of outbound links of A plus PR of B and outbound links of B. That is, it will be 0.15 plus 0.85 of, what is PR of A? 1.05441875 by what is outbound links of A? Outbound links of A is 2. So 2 plus What is PR of B? PR of B is 0.5980802967 by outbound links of B is 1. So now let us calculate all those things. 0.590, it will be 0.15 plus 0.85 of, so let us try to do this. 1.0541875 divided by 2, so it's to this much. So the solution is this much, and now we will be adding this 0.59802967. so we got solution of 1.1 into, now we have to do with the 0.85, which results to 0.9. we have to add 0.15, so we got a solution of 1.1106. So let me calculate it again. So for A we got 1.0541875 divided by 2, we got 0.52. now we have to add this value plus 0.59802967. so for the entire this one we got 1.125 into 0.85, 0.956. so this total term is known as 0.956354921. so now we have to add 0.15 to it. we will be getting 1.106354921. so PR of C is equal to this much. so this is a level 2. so now we can see that all the values are somewhat the other changed. One, it is 1.05, it is 0.5, 1.06. in case if you need to do it more for level 2, this is level 2, we have to extend it for level 3, level 4 as well, but we will be stopping it here because it will be more lengthy problem if we do that.